Okay, so in this video we are going to continue working on a problem that we have looked into in an earlier video, and the problem goes as follows. So there is a uniform bar that is resting vertically on the ground. So it is just in a very fragile equilibrium, let us assume, and it has a mass m and length L, and at this initial instant there is impulsive force that acts at the bottom of the bar, and the bottom of the bar gets a velocity v naught. So the question says, what is the angular velocity of the bar immediately after this impact, or immediately after this impulse, and also what is the horizontal velocity of this bar immediately after this impulse. So here is the approach that we took to solve this problem in the part 1 or prior video. And the approach that we took was that we wrote the linear impulse momentum equation and the angular impulse momentum equation. And then we also kinematically linked the velocity of the bottom with the velocity of the center of mass at the instant of the impulse with the initial angular velocity. And that gave us 3 equations, and we were able to solve for the initial angular velocity and also for the initial velocity of the center of mass. Now, in this video, we also went on to demonstrate how the results would change if instead of a uniform bar, it was 2 particles connected by a rigid massless link. So this extension was done here, as you can see. So you'll find the details of this problem and the extension of the problem in the prior video, part 1 of this problem. In this video, what we are going to do is we are going to explore a different way of writing these equations. Specifically, we will explore a different way of writing the angular impulse momentum equation. And we will show that we get the same results, of course. But before we do that, let's just briefly talk about this angular impulse momentum equation. The fundamentals of this angular impulse momentum equation is important because the equation that we are using here is that the angular impulse that is formed by this impulse, impulsive force F hat, is being equated to the change in the angular momentum, right? So now the important thing to note here is that this equation is written with the point of interest to be the center of mass. And that is evident because the moment of inertia is about the center of mass, and the angular impulse that is being calculated here is also about the center of mass. So that is the reason why we basically say that this is an angular impulse momentum equation that is written about the center of mass. Now, if you go to the fundamentals of this angular impulse momentum equation, you will see that typically this angular impulse momentum equation, or for that matter the overall angular equations of motion, are typically written about either the center of mass, number 1, or it is written about a fixed point. Okay, and the reason these two are typically chosen, one of these two is chosen, is because in these 2 cases the angular impulse momentum equation becomes simple, in the sense that in both these cases the change in angular momentum is equal to the angular impulse about that point of interest. So if it is the center of mass, the angular impulse is calculated about the center of mass. If it is a fixed point, the angular impulse is calculated about that fixed point. Okay, and that is equated to the change in angular momentum. So that is the reason why we choose either between the center of mass or a fixed point. Typically for rigid bodies in three-dimensional space, it is easier to choose the center of mass of the rigid body. And in fact, we choose typically coordinate system that is fixed to the rigid body. So it's a body fixed coordinate frame. But in any case, so that is the reason why we either choose the center of mass or we choose a fixed point. Now, if you choose any other point, any other point of reference, then you have to keep in mind that this equation starts getting extra terms. When you write the angular, the equation of motion in the angular directions, then it is not just rate of change of angular momentum is equal to the moment of all external forces and torques. There are extra terms that get added. So that is the reason why either the center of mass is chosen or a fixed point is chosen. Now, what we want to do in this part of the problem is we want to now change the angular impulse momentum equation by writing it about a fixed point. We will see that in this case, it has got a certain minor advantage. We will look into that. It's not a significant advantage, but the more important thing is to show that if we choose the reference point to be a fixed point, then we will get the same answer. We will, however, have to judiciously choose that fixed point. So that is what we are going to do in this part of the problem. All right. So, so this is going to be method 2. And here we will do angular impulse momentum about a fixed point. Okay, so our problem remains the same, a vertical bar which is delicately balanced on a horizontal surface. The vertical bar is of mass m and length L. It's a uniform bar. And there is an impulse that acts at the bottom, which causes instantaneously the velocity to go from 0 to V0. Let's say this is our x direction, and let's say this is the direction of angular displacement. This is the center of mass, which is at the geometric center. We want to find out what is determine, and the velocity in this direction is Vc. So determine Vco and theta dot O. Initial values just after impulse is applied. All right, so let us draw the free body diagram. So we are considering the instant when the impulse is applied. At that instant, the gravitational force is vertically, of course, it's always vertically downwards, but at that instant, it is along the same line as the normal reaction. And This is the impulse. Here is the center C. And the result of this impulse is the velocity v naught at the bottom, and the center of mass gets a velocity vc naught, and the bar gets an angular velocity of theta dot naught. Now, this is our x direction. So note that at the instant when the impulse is applied, the bar does not get a velocity in the y direction. And that is because if you write the equation of in the y direction for an arbitrary angle, you will see that when theta is equal to 0, the let me just think about it just a little bit. Yeah, so when the angle theta is equal to 0, what's going to happen is that the acceleration in the y direction is going to be equal to 0. And that means that there is no velocity change that will happen in the y direction. Of course, as the angle theta changes and it's falling down, then you will have a scenario where there is a velocity generated in the y direction, and that velocity will change because it's falling now. But initially, there'll be no change in velocity at the instant when the impulse applies. So therefore, with respect to the linear impulse momentum equation, we can just write the equation in the x direction. So we can say that f hat is equal to mvc naught. Right? And you will see that this is the same equation that we had in our in method 1, the first part of this problem. Now, when it comes to the angular impulse equation, angular impulse momentum equation, in this case, what we'll do is we'll choose a fixed point on the ground. Okay? And let's say that this fixed point is here. Let's call this point O. And let's say that it is, this point O is at some distance x from the bottom of this bar. All right. So this is a fixed point. This is a fixed axis x, and so let's say this is my fixed x-axis and this is my fixed y-axis. So the point O is a fixed point. Now, if I apply the angular impulse momentum equation about this fixed point, I will still have the same thing, that is the change in angular momentum about the point O is equal to the net angular impulse of all these forces about the point O. So note that, in this case, note that mg is equal to n. So mg and n, the forces cancel and they do not produce any angular impulse about the point O. Okay? Previously, about the point C as well, they did not produce any impulse because these forces were passing through the point C at the instant when the impulse is applied. At the point, about the point O also, the impulse produced by mg and n at that instant when this impulse f hat is applied is 0 because mg and n are balancing each other. Furthermore, the other impulsive force, that is f hat, is also not producing any impulse about the point O, angular impulse. And that is because f hat is going through the point O. So it has no moment arm. So therefore, we note that about O, the angular impulse is 0 at this instant. And by this instant, we mean the instant when F hat is being applied at the ground and when the bar is vertically upright. So what this means is that, therefore, angular momentum change is 0 about O. So what this means is very interesting. Initially, the bar, when it was resting vertically upright in a fragile equilibrium, it had 0 angular momentum about O. After the impulse is applied, the angular momentum that will be produced due to this impulse about the point O will also be equal to 0. So angular momentum is conserved. That is, angular momentum is conserved about O at the instant when F hat is applied and bar is vertical. It is very important to note that the angular momentum is conserved about O at this particular instant. And it is this particular instant that we are interested in because we want to know how much is the change in velocity of the center of the bar and the angular velocity at this instant when the impulse is applied. So it is just before, infinitesimally before the instant and infinitesimally after the instant where the angular momentum is conserved about the point O. Okay. So now let us see the initial angular momentum is equal to 0. So therefore the final angular momentum just after the impulse is applied is also going to be equal to 0. So now what is the angular momentum of this bar about this point O? So the angular momentum H about O is going to be H about C, right, plus R cross M V C. This is saying that the angular momentum about this point O is equal to the angular momentum of the bar about its center of mass plus the R cross MVC. Okay, and in this case it's going to be MVCO because we are interested to find the expression at that instant, or the value of the angular momentum at the instant when the impulse is applied. Right? Now, what is HC? HC, in this case, these vectors become very simple because all the rotations are happening in this plane, which means that the rotation vectors, the angular momentum vectors, are all perpendicular to the plane of this page. So there is just one direction of the angular momentum, and that is the Z direction. So that's why it is quite simple. It is HC is going to be equal to the moment of the angular momentum of this bar about the center instantaneously, immediately after the impact, is going to be 1/12th ml squared. That is the moment of inertia about the point C times theta dot O. Okay, and just to complete the expression, this is going to be in K because XY will produce Z in the upward direction according to a right-handed coordinate system, and that's the direction we have given for the angular velocity. So we have this. Now R cross MV is basically the angular momentum that is produced by the velocity of the center of mass about the point O. So you can do this. The R vector is going to be, so this R vector is essentially going to be xi plus L by 2j. Okay. And VCO, the vector, is going to be basically VCO, the magnitude in the I direction. So if you do this cross product, you will get that the angular momentum, so this R cross M VCO is going to be essentially, and you can see it from the diagram, it is basically this velocity and it is producing a moment arm in the clockwise direction. So it is going to be minus L by 2 M VCO in the K direction. All right. So therefore, the angular momentum about the point O is going to be 1/12 ml squared theta dot O minus ml over 2 VCO, and this whole thing is going to be in the K direction, and that is going to be equal to 0. This is the angular momentum conservation. Right, which the observation that we made over here. So then, proceeding with this, then we can say that therefore 1/12 ml squared theta dot O is equal to ml over 2 VCO. Cancel the m, cancel 1l, and then we have the expression 1/6 L theta dot O is equal to VCO. All right. So here we have our first equation, and here we have our second equation. Okay. And our third equation is going to be basically the same kinematic equation, which says that the angular velocity that is generated as a result of this impulse is nothing but VO minus VCO divided by L over 2, right? And that just comes from the idea of instantaneous center. If you think about it, if you know the velocities at 2 points, then you can find out the angular velocity of the rigid body from those 2 velocities. We have theta dot O. So we'll say also theta dot O is equal to VO minus VCO divided by L over 2. And this is our equation 3. Right? So VO is given, V naught is given, VCO is what we are trying to find out, and theta dot naught is also something that we are trying to find out. So in fact, from here we get half L theta dot O is equal to VO minus VCO. You see? So from here, one thing that you see is that now the rotational equation has shaped up, the angular impulse momentum equation has shaped up in such a way that it does not have F hat in it. And so does this equation. This equation also does not have F hat in it. So we don't have to eliminate F hat as we had to do in the first part, where we used the angular impulse momentum. We wrote the angular impulse momentum equation about the center of mass. Here, there is a little bit of advantage, as you can see, but it's minor. There is really not too much of a difference, but it is getting us to the angular impulse momentum equation from a different perspective. So that is very important, and it is going to demonstrate that this is a valid way of getting at our solution. So from these two equations, without having to use the linear impulse momentum equation, we can find out the values of VCO and theta dot O. So let's do that. So you'll see basically that from 2 and 3, so let's call this 3 prime. So from 2 and 3 prime, we have, now this guy is 3 times that. So 3 times VC naught is equal to V naught minus VCO, right? Which gives us VCO is equal to 1/4 of V naught, which is the same answer that we got using the first method, where our angular impulse momentum equation was about the center of mass. And from this now, we can substitute this into equation 2. Therefore, from 2, we get 1/6 L theta naught is equal to 1/4 V naught, which implies that theta dot naught is equal to 6/4, which is 3/2, which is 1.5 V naught over L. Which is also exactly same as the solution that we got using our first method. So that is basically what I wanted to demonstrate. It's a relatively short video, but it is an important concept, because what it tells us is that what it confirms is that angular impulse momentum equations can be written about the center of mass, or it can be written about a fixed point. In this case, by writing the equation about the fixed point, we were able to eliminate, and choosing the fixed point on the ground. See, we chose the fixed point O on the ground. And with this, what happened is that about this point on the ground, or for that matter, any point on the ground, the angular impulse due to all these external forces was equal to 0. And because of this, we had, for that instant when the impulse is applied, we had conservation of angular momentum. Essentially, the angular momentum that was produced by the rotation is exactly equal to the angular momentum produced by the forward going force about this point O. And that is the conservation of angular momentum that is being valid here. And from there, we are able to find out the values of this initial angular velocity and the initial velocity of the center of mass. So that's so it highlights important aspect of rotational equations, angular impulse momentum equations that are so important, indispensable for analyzing motions of rigid bodies. So that's it for this video. Thank you so much.